Hello, my darlings. Okay, so today we're going to look at a specific type of differential equations. We're going to look at growth and decay. So let's consider the statement, the rate of change of some quantity y, so the rate of change of a quantity y is dy dt, is directly proportional to, we write equals a constant, and it's directly proportional to y. So dy dt equals ky. If y is a differentiable function of t such that y is greater than 0 and y changes at a rate proportional to the amount present, that means we have this differential equation dy dt equals ky, and k is a constant. Then we know by the law of exponential change and the fact that we've already solved this a few times that y equals y naught e to the kt. Okay, where y naught is the initial value, that means it's the value of y when t equals 0, when time is 0, and k is the constant of proportionality. When k is greater than 0, we have exponential growth, right? Because if you raise e to a positive exponent, it grows. But if k is negative, so you have e raised to a negative exponent, then you have exponential decay. Okay, now you might remember this equation from pre-calculus. We use that a lot in pre-calculus for exponential growth and exponential decay. You might even remember that it's related to the interest formula, the PERT formula for compounding continuously. This also follows the law of exponential change. Okay, that's where it came from. So now we're going to prove this. Last year we accepted that exponential growth and decay followed the rule y equals y naught e to the kt. We're now going to prove that if something changes at a rate proportional to itself, that it supports that model y equals y naught e to the kt. So in order to solve a differential equation, we're going to separate our variables. We need to move all the y's to one side. Now we have no t's, but I'm going to keep my constant where it is. I like to keep my constant with my independent variable usually. So I'm going to have dy, and I have to divide by y equals k, and we multiply by dt. Now we're going to integrate both sides. So the antiderivative of 1 over y is the natural log of the absolute value of y equals k times the antiderivative of t, or the antiderivative of k dt is t plus a constant. And I'm going to call it C1 because I know it's coming. Now this example, though it seems very simple, has a few tricks in it that are very, very important. Okay? Now, in order to solve for y, we'd have to get rid of the natural log. So to solve a log equation, we change it to exponential form. That means the absolute value of y equals e to the kt plus c1. Now, if we want to solve for y, we'd have to lose the absolute value symbol. But that means the other side could be positive or negative. And the other thing I want to look at here is if I have addition in an exponent, it means I used to have e to the kt times e to the c1, okay? Now, notice I used pink and blue. Everything that's in the pink is a constant. The positive or negative 1 and the e to the c1. Those are all constants, and constant times a constant is another constant that I'm going to call c2 times e to the kt. Now, why did I do that? Because it's much simpler to solve this than it is to solve that messy thing, okay? All the plus and minuses and the e raised to the exponent is all wrapped up into one nice, neat constant now, okay? Now, and that's our solution, but wait a minute, is that y equals y naught e to the kt, right? The question is C2 y naught? So let's take a look. If we let t equal 0, then y would equal C2 e to the 0, and e to the 0 is 1, so y equals C2. So that means that C2 is indeed our initial value, which we call y naught. So therefore, we have proved that the solution is y equals y naught e to the kt. t. So now, anytime you have dy dt equals ky, you can automatically jump to the solution y equals y naught e to the kt. So now let's use this, and honestly, this type of growth, exponential growth and decay, we talked about this in pre-calc, occurs all the time in bacteria growth, population growth, growth of money, in computing. It's used in all kinds of applications, okay? So here's one where the bacteria in a certain culture increase continuously, just like compounding continuously, at a rate proportional. So let's use y for the number of bacteria. dy dt is proportional to the number of bacteria present. So there we are, dy dt equals ky, yay. Now, if the number triples in 6 hours, so that means y of 6 is 3 times the amount that it started with, okay? How many are there in 12 hours? So that means we're looking for y of 12. So now, since we know our differential equation is dy dt equals ky, we know that the solution is y equals y naught e to the kt. Now the problem is we don't know what y naught is, nor do we know what k is. So we're going to use what we do know. We're going to use the fact that y of 6 equals 3y naught, and we're going to plug that in to our solution. So we would have 3y naught equals y naught e to the 6 times k. Now, if you notice, there's a y naught on each side, which will divide out. So now we have 3 equals e to the 6k. When we have an exponential equation, we need to change it to a log equation. So the base is e, log base e is natural log of the 3 equals exponent 6k. Now to solve for k, all we have to do is divide both sides by 6. Now I'm going to caution you here. Even if it's a calculator problem, yes, I know you could put this in the calculator up here at 3 equals e to the 6k and get a decimal, but you need to use the entire length of the decimal in any other computations. You'd have to store that in a variable and write down more than 3 decimal places when you write it on paper, because remember, you're not allowed to round until the end of the problem when we're getting the answer. And if you round right here, you're going to have an incorrect value. Okay, so please keep that in mind. So now I can take that and plug that into my solution, and I have y equals y naught e to the k times t. So that means I have t natural log of 3 all over 6 in my exponent. Wow. Now I'm supposed to find y of 12. So y of 12 would be y naught e to the 12 times the natural log of 3 over 6, which is y naught e to the 12 divided by 6 is 2 natural log of 3. Now I need to simplify that exponent. So it's y naught e to the, remember, if you have a number in front of a natural log, it used to be the exponent. So this is really y naught e to the natural log of 9. And remember also that the exponentials and the logs are inverse functions. So this just becomes y naught times 9, or 9y naught. So y of 12 is 9y naught. What does that mean for us? That means in 12 hours, there will be 9 times the original amount of bacteria. Okay. Now there's another part. It says, in how many hours will the original number quadruple? So now we want to know the t when y is quadruple, means 4 times y naught. So remember, that would be the y value is 4y naught equals y naught e to the t natural log of 3 over 6. And again, we have a y naught on both sides, so they're going to divide out. Okay, so now I have 4 equals e to the t natural log of 3 over 6. I have an exponential equation, which I changed to a log equation. So that's the log base c, which is the natural log of 4, equals the exponent t natural log of 3 over 6. Now to solve for t, we'd have to multiply it by 6 and divide by the natural log of 3 on both sides. That means that t is going to be 6 times the natural log of 4 all over the natural log of 3. That's our exact value, which isn't really helpful, so I'm going to put it in my calculator here. And that's approximately 7.571 hours. There we go, guys. All right. Have a great day, and I'll see you soon. Bye.